This video covers section 4.1, solving systems of linear equations by graphing. Objective 2, solve a system of linear equations by graphing. When looking for a solution to a system of equations, we're looking for a point or points that satisfy both equations. A point satisfies a single equation if it's a point on its line. A point satisfies the other equation if it's a point on its line. It satisfies both equations simultaneously if it's a point on both lines. So the idea then is to graph both of these lines and see where they intersect if they do. Luckily for us, both of our lines are in their point slope form, so we graph them. The first line has a slope of -2, and the second line has a y-intercept of 0, 9. So we go up to 0, 9. And now we use a slope of -2. We rise -2 and run 1. Rise -2 and run 1. Rise -2 and run 1. -2 and 1. And keep going until we get the entire graph of the line. Or up 2 and left 1. And we connect the dots with a solid line. And those are all the points that satisfy the first equation. The second equation has a slope of 3 and a y-intercept of 0, -11. We'll start at 0, -11, and then we'll rise 3 and run 1. Continue until we possibly see the point of intersection. And now I'm done because I see it landed right on top of that other line. So at this point, I say it looks like the point 4, 1 is a solution. And I put eyes on there because it kind of looks like it right now. So we should check. Should always check these because you can always make sure that it's right. And if it doesn't work out, then it's obviously wrong and we can fix it. So plug in 4 to the first equation. -2 times 4 is -8. Plus 9 is 1. Works in the first equation. Second equation is 3 times 4 is 12 minus 11, which is 1, and it works in the second equation. Now I can be confident in saying that 4, 1 is the solution. This graphing technique is a really nice technique to give us a pretty picture of what's going on. The point of intersection is the solution. Example 3, same thing, but this time they're not in our slope-intercept form. We know to graph these lines, it's much easier to write them in slope-intercept form. 4x plus y is -3, and 5x minus 2y is -20. My first equation to write in slope-intercept form, I subtract 4x from both sides. My second equation, I subtract 5x from both sides. But then I have to divide by -2. That gives me y equals negative 5 over negative 2, which is positive 5 halves, and negative 20 over negative 2, which is plus 10. So I graph both these lines separately. The first line has a slope of negative 4 and a y-intercept of 0, negative 3. I go to 0, negative 3, and the slope is negative 4 over 1. So I rise negative 4 and run 1. Rise negative 4 and run 1. Rise 4 and run left 1. Rise 4 and run left 1. Continuing up, 4, left 1, and there's my line. Graphing the second line, we have a slope of positive 5 halves and a y-intercept of 0, 10. So I go up to 0, 10, and I rise 5 and run 2, which will put me off my graph paper. So I rise negative 5 and run left 2, right on top of that common point. Connecting those dots, I get what looks to be the point of intersection, negative 2, 5. At this point, I say it looks like negative 2, 5 is the solution. And I'll be confident it is the solution once I check it. The first equation, 4 times x, 4 times negative 2, plus 5 is negative 8, plus 5, which is negative 3. That works. Second one is 5 times negative 2 is negative 10, minus 2 times 5. That's negative 10 minus 10, which is negative 20. Works in the second equation. So now I can be confident that negative 2 comma 5 is the solution. Example 4. Solve the system by graphing. The first equation is ready to go. We see that it has a slope of 3 and a y-intercept of 0, 1. My second line, 2y minus 6x equals 14. I add 6x to both sides and divide everything by 2. This line has a slope of 3 and a y-intercept of 0, 7. Graphing the first line, going up to 0, 1, and using a slope of 3. Rise 3 and run 1. Rise negative 3 and run left 1. Graphing my second line, this one starts at 0, 7. But its slope is 3, so I rise 1, 2, 3 and run 1. 1, 2, 3 and run 1. Or down 3 and left 1. And it doesn't take long to realize that those two lines are parallel. In fact, you probably noticed even before I graphed them that they were parallel. Because they had the same slope, different y-intercepts. That is a set of parallel lines. When you have parallel lines, they never intersect, which means there is no common point of intersection. So we write no solution on these. And then the last example, we solve this one by graphing. My first equation is negative 4x minus 2y is negative 8. My second line is 2x plus y equals 4. In my first line, I add 4x to both sides and divide by negative 2. Gives me y equals negative 2x plus 4. My second line, I subtract 2x from both sides, and that gives me y equals negative 2x plus 4. My first line has a slope of negative 2 and a y-intercept of 0, 4. And my second line also has a slope of negative 2 and a y-intercept of 0, 4. Those are the same exact line. Slope of negative 2. So when we graph the first line, we get that one. And when I graph the second line, they're right on top of each other. So where do the lines intersect? There isn't a common point this time. There are common points. So instead of describing what points they are, we just go ahead and say there are infinitely many points of intersection. Or we say infinitely many solutions. So in this case, there are infinitely many solutions because our two lines were the same exact line. This concludes the video for section 4.1, solving systems of linear equations by graphing. Objective 2, solve a system of linear equations by graphing.